I would pause the video and try this warm up. I've given us a table with the ordered pairs for x and for y. I want you to complete synthetic division to solve the polynomial. So hopefully you noticed that you should have zeroed in on when you put in a number for x, we wanted to get y. We wanted to get a remainder of 0. So notice that the table tells me that when I plug 1 in for x, I'm going to get 0. So because they gave us 6x cubed minus 11x squared plus 6x minus 1 as my polynomial function, I used synthetic division with the number 1 to test. And so that got me my 0 like it should have. And then I had my quadratic where I could either factor or do the quadratic formula to then find my other 2 zeros, because if it's a cubic, we should have 3 zeros. So 1, 1/3, and 1/2 end up being those answers. All right, so we're going to continue with section 3.4, which is zeros of polynomial functions. What we're going to be looking at today is we're going to use the linear factorization theorem to find polynomials with given zeros, and we're going to use Descartes' rule of signs. Properties of roots and polynomial equations. So in our last lesson, we learned that all the zeros of polynomial equations, which we could also sometimes refer to as roots, so zeros, roots, those are interchangeable, they did not have to be real numbers. Okay, we did get an answer where we had an imaginary number. So therefore, if a plus b is a root of a polynomial equation, then the imaginary number of a minus bi is also a root. Okay, so we always had plus or minus because imaginary roots, if they exist in a conjugate pair. Okay, so remember conjugate when we were talking about like dividing like rational, when we were dividing square roots, or even when we were doing complex numbers, we had to multiply the top and the bottom by the opposite sign of whatever that term was in our denominator. We had the conjugate. All right, linear factorization theorem states, so once again, we just have this f of x function. So once again, that definition is just saying that you start with the biggest exponent, you're going in standard form down to the smallest, which is just a constant. We need n to be greater than or equal to 1. We don't want our lead coefficient to be 0. When that's the case, we're going to be able to factor. So the lead coefficient times a bunch of different binomials. Okay, C1, C2, C sub n, those are all complex numbers, so possibly real, not necessarily distinct. So in words, an nth degree polynomial can be expressed as a product of a non-zero constant and n linear factors. So if we're talking about an x squared term, like a quadratic, well then it'd be two different things being multiplied together. If it was a cubic, then we would have 3 things being multiplied together, and so on and so forth. So let's take a look at an example. It says find a third degree polynomial function, f of x, with real coefficients that has -3 and I as zeros, such that f of 1 equals 8. So there's a lot of things to kind of get out of this information. The first thing that it says is that it wants us to find a third degree polynomial. So that means that if it's a third degree, we want our answer to be an x to the third power. Okay, so n equals 3. That is what our exponent, the biggest exponent, should be. So if that's what our exponent should be, that means that technically we have 3 zeros. So we need to have 3 things being multiplied together in order to get us our polynomial. Right now, they've only given us 2 zeros. They gave us -3 and they gave us I. Well, if my zeros are -3 and I, remember, an imaginary number has a conjugate. And so if I have a positive I, that means I need to have a negative I as well. So the moment I have one imaginary number, I need the opposite sign of that same thing as well. So that is my 3 zeros. And then the last thing they tell us is that f of 1 equals 8. we're going to use that information later on down the road. So first thing that I want to focus on is the fact that we're trying to create this f of x polynomial function. I don't know what my lead coefficient is, so we're going to keep it as a sub n. But then I know that I'm going to have 3 factors because we want degree 3. And so it's going to be x starting us off, and it's always going to be x minus our 0. So if one of my zeros is -3, x minus -3, if I subtract a negative, I should have a +3 in the parenthesis. Okay. If my next 0 is I want x minus I. If my last 0 is -I, I should have x minus -I. If I subtract a negative, it makes a positive. So whatever signs my zeros are, those need to then essentially be the opposite signs when we put them into our factored form. So now I'm going to start distributing. So I'm going to keep that lead coefficient. Right now, I'm going to keep this x plus 3 as well. Anytime I have imaginary numbers, I'm going to start by multiplying those because then eventually the imaginary numbers should disappear. So if I start multiplying, x times x is x squared, x times I is ix, negative I times x is negative ix, and a negative I times I is a negative I squared. Notice that my middle terms of ix are going to cancel. So that still leaves us then with x squared. And then remember, anytime I have an I squared, it's really -1. So I'm subtracting -1, which is why then it becomes +1. I'm going to go ahead now, and I have no more imaginary numbers. I can now multiply these two binomials together. So x times x squared is x to the third. X times 1 is 1x. 3 times x squared is 3x squared. And 3 times 1 is 3. All right. Once I've gotten to this point, now I'm going to use this information that f sub 1 equals 8. That's going to help me determine what my lead coefficient a sub n is. So what I'm going to do is I know that I am going to have this equal 8. I don't know what a sub n is, but I know that x I'm going to be replacing with the number 1. So we're going to have 1 being cubed plus 1 plus 3 times 1 being squared plus 3. So if I start simplifying everything in parentheses, well, 1 cubed is 1. Add 1, we'll get 2. 1 squared is 1 multiplied by 3. So we'll have 1 plus 1 plus 3 plus 3. So that's going to give me 8. And so a sub n is being multiplied by 8. So that gives me 8 a sub n. So last step is then let's divide by 8. And I now know that my lead coefficient is actually a +1. Okay, so once I have what that a sub n is, I now am going to have everything that I need to write what my actual answer is. So what I'm going to do is I'm going to go back to this part right here prior to me substituting in the numbers from that f sub 1 or f1 equals 8. Okay, so I'm going to be able to now replace a sub n with 1. Everything else is the same. If I distribute 1 to everything in parentheses, nothing's going to change. So the only thing I'm going to do with this function is I'm just going to rewrite it in standard form. So notice how x to the third, I should have a third degree polynomial. Then I'm going to say plus 3x squared plus x plus 3. Now, had that a sub n been like the number 2, I would distribute 2 to all of those terms. And so we would have had 2x cubed plus 2x plus 6x squared plus 6. And then I would have rearranged that to be my final answer. But since it was 1, it didn't change any of those numbers or any of those terms. I just wrote it in standard form. So there's my function that meets all of the descriptions from the given information. It's a third degree polynomial. If I was to factor that, I'd get my 3 zeros of -3, I, and -I. And then if I substitute in 1, I'm going to make that equal 8. Okay, let's try another example. It says find a 4th degree polynomial. So I know that n is going to equal 4 here. Our coefficients for our zeros are going to be -2, -1/2, and I. We know f of 1 equals 18. So once again, I know that if n equals 4, I should have 4 zeros. Well, right now, my zeros are -2, -1/2, and I. That's only 3. But the moment I have an imaginary number, I need its conjugate, so I also need -I. So I know that when I start writing my function, a sub n is unknown to me, but I know that I have to have 4 things being multiplied together since I want degree 4. So I'm going to have x minus -2. If I subtract a negative, it's going to give me a positive. The next thing I'm going to have is -1/2. But think about this. How did I get -1/2 as a 0? Well, I set up a factor, which I now am going to be writing, and I set it equal to 0. So if I know that x equals -1/2, kind of work backwards to make it equal 0. That means I multiply both sides by 2 to get rid of the fraction. So 2x equals -1. How do I make this equal 0? Well, I add 1 to both sides. So that means my second parenthesis was 2x plus 1. That's how I got to this 0 of -1/2. My other zeros would be x minus I and x plus I, because once again, I subtracted that -I. All right, now that I have those, I'm going to start actually multiplying out my binomials. So I'm going to start with my imaginary numbers. So once again, x times x is going to give me x squared. The i's are going to then end up canceling out because remember, these are conjugates. So the i's cancel out. And so the last thing I have is -I times I. So that's -I squared. But I squared is the same thing as -1. So when I subtract -1, I'm going to get +1. I'm going to go ahead and I'm now going to start multiplying the first two binomials together. X times 2x is 2x squared. X times 1 is 1x. 2 times 2x is going to give me 4x. 2 times 1 is going to give me 2. I can start combining like terms. So we're going to have a 2x squared plus 5x plus 2. And now I have 2 more polynomials to multiply together. So I keep that a sub n, but now I multiply 2x squared times x squared. So that gives me, 2x to the 4th. We have 2x squared times 1, so 2x squared. We have 5x times x squared, so that gives me a 5x to the 3rd. We have 5x times 1, so that's 5x. We have 2 times x squared, so that's 2x squared. And we have 2 times 1, so 2. All right. If I start combining like terms there, we'll have a 2x to the 4th. Looks like we've only got 1x cubed. So we'll have 5x cubed there because there are no like terms. I've got a couple of x squared. So when I combine that, it gives me 4x squared. Looks like we don't have any extra x's, so it's just 5x, and then it looks like it's just 2. All right. So once I've gotten to this point, now I want to use the information that f of 1 equals 18. So if I wanted to equal 18, I don't know what a sub n is, but I know that I'm going to substitute 1 in for x. So we'll have 2 times 1 to the 4th, plus 5 times 1 being cubed, plus 4 times 1 squared, plus 5 times 1 plus 2. All right, so essentially all of those are being multiplied by 1, so it's not going to change the numbers. So we got 2 plus 5 plus 4 plus 5 plus 2. Add all that up, and you get 18. So 18 gets multiplied by a sub n. So once again, divide both sides by 18, and we'll get our lead coefficient to be the number 1. So now both examples have been 1, but I do want you to be aware that that doesn't necessarily mean that you're always going to get a lead coefficient of 1. So please do not assume that. Okay, sometimes a sub n could be 2, or it could be -1. It really depends on the problem. So remember, I'm going to go back to what I had prior to plugging in the numbers, and that was this right here. Okay, but now I know that a sub n is 1. So if I was to distribute a 1 to everything that I have in parentheses, it's not going to change anything that was in that parentheses. So that means that my final polynomial function is going to be 2x to the 4th plus 5x to the 3rd plus 4x squared plus 5x plus 2. It's a 4th degree polynomial. It would, if we solved, have our zeros, which are -2, -1/2, I, and -I. So that is our function. All right, let's talk about Descartes' rule of sign. So it says we're going to let f of x equal that polynomial expression. So once again, standard form, biggest degree down to the smallest. We've got real coefficients. So it says that the number of positive real zeros of f is either going to be the same number of sign changes of f of x, or it's going to be less than the number of sign changes by a positive even integer. The other is that to have a negative real zero, it's either going to be the same as the number of sign changes for f of -x, or it's going to be less than the number of sign changes of f of -x by a positive even integer. If f of -x has only one sign variance, so only one variation in sign, that means f has exactly one negative real zero. All right, let's look at an example of what that all means. So we're going to determine the possible numbers of positive and negative real zeros of f of x equals x to the 4th minus 14x cubed plus 71x squared minus 154x plus 120. All right, so let's talk about positive real zeros. That means we are looking at the function of f of x. So they gave us that function that is x to the 4th minus 14x cubed plus 71x squared minus 154x plus 120. So I'm looking for sign changes. So notice that the first term is a positive number, and then it goes to a negative number. That's a sign change. Then that second term is negative. It goes to a positive number. That's another sign change. Then it goes from positive to negative, and then it goes from negative to positive. So that tells me that there are 4 sign changes. And so when there are 4 sign changes, that means I could potentially have 4 positive real zeros. But I could also have a smaller amount, but it has to be an even value. So essentially what I have to do after I figure out this number is I have to keep subtracting 2 from it every single time until I can not have any more positive numbers. So 4 minus 2 means that I could potentially just have 2 positive real zeros. 2 minus 2 is 0, so that means I could have potentially 0 positive real zeros. If I tried to subtract 0 and 2, I'd get -2, and so that means that I can no longer keep subtracting 2. So these are all my possible number of positive real zeros that I could have in this problem. Okay, now I want to look at negative real zeros. To look at the sign changes, we have to look at f of -x. So that means that I have to go into this original f of x function, and I have to substitute in -x into all of the x's to figure out then what my function is. All right, so if I raise a negative term to the fourth power, it's going to give me a positive. If I cube a negative, it's going to give me a negative. But since then that's being multiplied by negative 14, we'll have a positive 14x cubed. If I square a negative, it's going to give me a positive. It's being multiplied by a positive number. When I multiply two negatives, it's going to give me a positive, and we didn't do anything to the last number. So notice that I go from a positive to a positive to another positive to another positive to another positive. So that means that there are 0 sign changes. Everything is positive. And so if there are 0 sign changes, that means that we have no negative real zeros. So there are none. And that is going to be useful information, because if I was then to actually ask you to find the zeros, if I was first and foremost, I'd have to list all my possible rational zeros, and that would be both positive and negative numbers. But if I know that there are no negative real zeros, that means that I should really only be testing positive numbers. I wouldn't want to go the route of negatives. So that's the idea behind this. Let's take a look at another example. We're going to find all the zeros, but we're going to use that idea of not only the rational zero theorem, so we know what numbers to test, but also this Descartes rule of signs to know, hey, maybe there's going to be more positive zeros than negative zeros, so maybe we should go the positive route versus the negative route, or vice versa. All right, so we're looking at f of x equals 2x to the third minus x squared minus 9x minus 4. So let's talk about first finding all possible rational zeros. That means I need to think about P over Q. So I need to know what's my P value, what's my Q value. So my P value is 4. So I'm thinking 1, 2, and 4. Those are going to be all of the factors of P. Q is 2. So that means it's 1 and 2. So that means that plus or minus, if I do 1 over 1, I'm going to get 1. If I do 2 over 1, I'm going to get 2. If I do 4 over 1, I'm going to get 4. If I go then 1 over 2, I'll get a half. If I do 2 over 2, I'm going to get 1, so I don't have to write that again because I already have it. If I do 4 over 2, I'm going to get 2, so I don't have to write that either. So that means that these are all my possible rational zeros. So now let's talk about how many positive real zeros will we have versus how many negative real zeros could we possibly have. Okay, so positive real zeros, means that we're looking at the sign changes of the function that I have listed here. So notice how we go from a 2 to a negative 1, so that's a sign change. But then we stay negative, we stay negative. So it looks like there is really only one positive real zero in this whole entire function because there's only one sign change. So now let's talk about negative real zeros. That means I need to look at f of negative x. So that means I want 2 times negative x being cubed minus negative x being squared minus 9 times negative x minus 4. So if I cube a negative, it's going to give me a negative. So we'll have negative 2x cubed. If I square a negative, it's positive, but I'm still subtracting it. So minus x squared. A negative times a negative is a positive. And then we'll still have minus 4. So I go from a negative to a negative, so no sign change. But then from there, I go to a negative to a positive. That's a sign change. I go from a positive to a negative. That's another sign change. So because there are 2 sign changes, that means I could have 2 negative real zeros, or 2 minus 2 is 0, so I could potentially have no negative real zeros. All right, so With that information, now let's go ahead and start actually testing numbers to figure out what my zeros are. So I'm looking and I see that, hey, I have no missing terms. My rule says start with the number 1. I'm going to start with that positive 1 just because I do technically have one positive real zero, because maybe then it's 1 and then we already found that. So I know I'm going to have 2, -1, -9, -4. All right, so let's start testing. Bring down the 2. 2 times 1 is 2. Add that up, I get 1. 1 times 1 is 1. Add that up, I get -8. -8 times 1 is -8. Add that up, we get -12. So unfortunately, 1 doesn't work. So then it's the route of, okay, what should we do? Should we go the positive route and keep trying to find that one real zero? Or do we kind of go the negative route because there is potentially 2 negative real zeros? And then the only other thing is that we could potentially have no real zeros. So that's my only hiccup in this plan. I mean, I would say that the odds are probably better because we have possibly 2 negative real zeros. I would say maybe we should go the negative route. Okay, so if I start, I could either do -1, -2, -4, -1/2. So it doesn't really matter if we try like -1. We're going to have 2, -1, -9, -4 again. So bring down the 2. 2 times -1 is -2. Add that up, we get -3. Multiply that, we're going to get +3. Add that up, we get -6. -6 times -1 is +6. Add that up, we get 2. So unfortunately, we did not get another 0. So that means that we have to keep testing. I'm going to test -1/2. All right. So bring down my lead coefficient. 2 times -1/2 is going to be -1. Add that up, I get -2. -2 times -1/2 is going to give me +1. Add that up, I get -8. -8 times -1/2 is going to give me +4. There's my 0. Okay, so that means that if one of my answers is -1/2, that means I'm going to have to also have another -0 because I should then have 2 negative real zeros. And then that means that we'll have 1 positive real zero. Okay, so now I get to rewrite this as 1 degree less. So since we started with an x cubed, now we become x squared. So 2x squared minus 2x minus 8 equals 0. It's a quadratic, which means we can either try to factor or we can take the square, or we could do the quadratic formula. Okay, if we try to factor, we do have a GCF here. So that means we'd have x squared minus x minus 4 left over. Hopefully you notice, though, there is no number that multiplies to -4 that adds to -1. So unfortunately, the factoring route doesn't work. So A is going to be 2, B is going to be -2, C is going to be -8. Let's do the quadratic formula. So we're going to have -b plus or minus, under the square root, we will have b squared minus 4 times a times c, and that's all divided by 2 times a. So back-to-back negatives makes that first 2 positive. Square -2 will have 4. I have 2 negatives that are getting multiplied together. Essentially, 4 times 2 is 8, and 8 times 8 will have a positive 64. That's all being divided by 4. If I add the numbers under the square root, that gives me the square root of 68. That's not a perfect square. However, this is going to be able to get broken down to get me a perfect square. This is 4 times 17. 4 is a perfect square, so that means this is really then 2 root 17. And so if I break it up, 2 over 4 plus or minus 2 root 17 over 4, both of those are divisible. So it's really 1/2 and 1/2 with the square root of 17. So that means my other answers are 1 plus or minus the square root of 17 all over 2. Okay, so there's my other negative 0, and there's my other positive 0, and there are my 3 zeros because it is degree 3. So that's us using the linear factorization theorem to find polynomials with given zeros and using Descartes' rule of signs.